On the channel. In today's video, we're going to be taking a look at question 5 from the QCAA Physics External Exam for 2021, paper 2. Now, you would have noticed on the channel, I've started splitting up all the questions into individual videos. That way, if you only struggle with a certain type of question, you can go watch that certain video for that certain question, rather than sitting through the full external exam. The full external exam is still up on YouTube though, so if you still need it, the link is in the description below, as well as the full playlist for each exam. If you guys need a physics external exam bundle pack, the link is also in the description below, so get your download while you can. But otherwise, let's get straight into this question here. And if you have any questions at all, leave something in the comments below or send me a direct email and I'll answer, okay? So, question 5. An alpha particle with a charge of this moves through an electric field, accelerating from rest through a potential difference of 240 volts. Determine the velocity of the particle at the end of its acceleration, expressing your answer in scientific notation. Okay, first of all, let's understand what we have here. So we have a alpha particle, which they say is positive, moves through an electric field, accelerating from rest with a potential difference of this. Whenever we have physics situations, we've always got to list what we have here. So they've said we have a potential difference, okay, which is the 240 here, which means we're going to probably have to use this formula here. So the potential difference is equal to your change in energy over your quote-unquote charge, okay? Now, the reason why we're using this is because of the electric field. However, we want to ask ourselves, why would we use this? Well, for starters, what do we have to find? So here, I'm just going to write this as just a change in work. It's the same thing otherwise. There's to determine the velocity at the end of its acceleration. So if we know it's at the end of its acceleration, that means it has just a constant velocity, which implies we can just use maybe the kinetic energy formula for this question here. But that's only because they said at the end of its acceleration. Otherwise, you might have to use other things here. Because they said accelerated from rest with that potential difference here, got up to a speed, and then probably stayed at that speed because they said end of its acceleration. You could use equations of motions here if you wanted to. However, there's an easier way to do it. Okay. So first of all, let's see what we've been given. We've been given the charge, which is 3.2 times 10 to the negative 19 coulombs. And we've also been given the V, which is the quote-unquote 240 V. So we could find the work here. And once we found the work, we know the work is the same as energy. And because it's moving, the particle, or the thing, the alpha particle, will have kinetic energy as well. Now, we could probably use this formula here because they said it's an alpha particle. We actually get given the mass of an alpha particle in our formula sheet. The mass of an alpha particle, if I just look here, what is it? 6.64 roughly times 10 to the negative 27 kilograms. So we can find the work, which we can then have this, and we then have that, and we can then find the velocity. So it's a pretty easy question when you think of it this way here. However, you've got to think of it that way in the first place. You could use equations of motion as well. So here we'll just set that equal to 240. So 240 equals change in work over the charge, which is 3.2 times 10 to the negative 19. Then you want to rearrange it to get the work or the energy by itself. So the work is the 240 times by the 3.2 times 10 to the negative 19. Then you'll chuck it into your calculator. So 240 times 3.2 times 10 to the negative 19. So this gives us the work or the energy, which is 7.68 times 10 to the negative 17, and that's given in joules. So here, we want to get the velocity by itself with the kinetic energy. Now, the reason why we're using kinetic energy is because it's moving. It's not stationary, so there's no potential energy. So here, to get the quote-unquote velocity by itself, you times both sides by 2, so 2 times the energy equals mass times the velocity squared. You'll then want to divide by the mass, so you have mass there, and then you'd probably want to square root to get the velocity by itself. So now we've just got to chuck all that information into that formula. Easier said than done. Let's just chuck it in. So we'll just make this smaller, move that up there. So velocity is the square root 2 times the energy, which was the work here, which is 7.68 times 10 to the negative 17, divided by the mass, which is the 6.64 times 10 to the negative 27. Now, like I said before, this is not the only way to solve it. you could use quote-unquote equations of motion. However, it might be a bit overkill here because it's only worth 4 marks, and the equations of motion would take a little bit more time than what we're doing right here. So remember, in an exam, you want to think of the most efficient way to solve a question if you know multiple ways to solve it. If you only know one way to solve it, go for it. You'll be fine with it. Okay, so this gives us a velocity of this, which is 152,093.8. Now, let's just write it in scientific notation because they're set up there. So we'll go 1, 2, 3, 4, 5. 1.52 times 10 to the 5, and that is meters per second. That's the velocity at the end of its acceleration. That's what we're assuming mainly there. Okay. If you have any questions about this one here, leave something in the comments below. If you want to send me an email, my email is also in the description of the channel. If you need a physics external exam bundle pack, the link is in the description below. But otherwise, I'll see you guys in the next video.